Hello, now we can start the solution of complex number. Exercise 2A, which is given in the classical algebra book written by S.K. MAPA. And the first question, we'll start question 1, 2, 3 and so on. The first question, question number 1. Question number 1. This is exercise 2A, S.K. MAPA classical algebra book. Classical algebra book, and this is basically on complex number. So here the question number 1 is basically let Z1 and Z2 are two complex number, be two complex number, then prove that the first question, Roman 1, Z1 Z2 bar plus Z1 bar Z2, this is less than equals to 2 mod Z1 multiple mod Z2. So first we will prove the question 1, Roman 1, then we will continue Roman 2 and Roman 3. So proof is basically here. Just you think about the left hand side. Left hand side is basically Z1 Z2 bar plus Z1 bar Z2. So this is left hand side. So this we can write it as 2 real Z1 Z2 bar. Z1 Z2 bar. And obviously you know the formula real Z, that real Z is basically less than equals to mod Z. So obviously this is less than equals to 2 modulus of Z1 Z2 bar, and this will be equals to Z1 bar and Z2 bar modulus. Now we know Z modulus and Z conjugate, that modulus is basically same. So we can write this is basically 2 mod Z1 into Z2. So this is basically the right hand side of the inequality. So we can conclude Z1 Z2 bar plus Z1 bar Z2. This is equals to less than equals to 2 mod Z1 into mod Z2. Now maybe the question arises for the first line, how we'll write Z1 Z2 bar plus Z1 bar Z2, this is equals to 2 real Z1 Z2 bar. Just think the one important case, the Z bar, that plus this is equals to 2 real Z. You know this formula. So here Z1 Z2 bar, you see Z1 Z2 bar plus Z1 Z2 bar rotor conjugate, whole conjugate, this is equals to 2 real Z1 Z2 bar. We just use this formula here. Now we'll move to the second question, and question number 1, Roman 2. We need to prove 1 minus Z1 bar Z2 modulus square minus Z1 minus Z2, that modulus square, this is equals to 1 minus mod Z1 square multiple 1 minus mod Z2 square. So this is also a simple question. I can prove it easily. Now we'll move to the solution. So 1 minus Z1 bar Z2, that modulus square, we can write it as 1 minus Z1 bar Z2 multiple 1 minus Z1 bar Z2 whole conjugate. Because we know the formula mod z square, this is equals to z bar. Here you can use this recall our formula. And now you will write it 1 minus z1 bar z2 multiple 1 bar is basically 1, z1 bar then whole bar conjugate, so it will be z1, so z2 conjugate. Since z1 minus or z1 minus z2 both conjugate, this is equal to z1 conjugate and z2 conjugate, and here we use z conjugate, then conjugate, that value will be z. We use this to result or properties of the complex number, and you can write it in that form. So now we just use the distributive condition or law, so 1 minus z1 bar z2 minus z1 z2 bar, and this will be plus mod z1 square z2 square. Again we use z bar equals to mod z square. So we have, therefore we have 1 minus z1 bar z2 whole square modulus whole square. This is equals to 1 minus z1 z2 bar minus z1 bar z2 plus mod z1 square multiple mod z2 square. So this is basically Roman 1. Again, I will move to the another terms here. Just you see the second part in the left hand side, z1 minus z2 whole square. So z1 minus z2 whole square, this value equals to z1 minus z2 whole conjugate. So that means z1 minus z2 multiple z1 conjugate minus z2 conjugate. So obviously this value is z1 whole square minus z1 z2 conjugate minus z2 z1 conjugate plus z2 modulus square. So this is basically Roman 2. Now we just see it the expression the left hand side. So we just expand this first expression and the second term. So we'll take the subtraction between first and second term, what we will get. So obviously by using 1 minus 2, we will get 1 minus z1 bar z2 whole square minus mod z1 minus mod z2 modulus whole square equals to, so it will be 1 minus z1 z2 bar minus z1 bar z2, and just we cancel this term and this term, so it will be z1 z2 bar plus and plus z1 bar z2. So obviously here you will see one thing, just I think means this quantity here, z1 bar square z2 bar square z2 whole square modulus minus mod z1 square minus mod z2 whole square. So this value will be just 1 minus mod z1 square minus mod z2 square plus mod z1 square multiple mod z2 whole square. So this is quite obvious. We can write it mod z1 square multiple 1 minus mod z2 square. So this is basically right hand side of our question paper. Just you see here, this is exactly given the right hand side. So therefore we have proved that 1 minus z1 z2 z1 by z2 that whole square minus z1 minus z2 whole square, this is equals to 1 minus mod z1 square multiple 1 minus mod z2 whole square. So proved. Now we'll move to the Roman 3. This is in obviously in question number 1. Roman 3, we have to show that 1 plus z1 bar z2, that modulus whole square plus mod of z1 minus z2 whole square equals to 1 plus mod z1 square multiple 1 plus mod z2 whole square. So just as question number previous question, what we have done, the solution, accordingly you will solve the question paper 1, 3. So you can solve it very easily. So this is basically self exercise. And I hope you will do it because it is as similar as the previous question. The solution looks like similar. So now we'll move to the question number 2, which is given in exercise 2a. Z1 and Z2, this is question number 2, are two complex number, or two non-zero complex number. It is given both the complex number and non-zero. Non-zero complex number, complex numbers, then prove that first question is Z1 by mod Z1, that quantity, modulus plus Z2 by mod Z2, this is less than equals to 2. And using this, you will prove the second part of this question, to mod Z1 plus Z2, that quantity greater than equals to mod Z1 plus mod Z2 by Z1 mod Z1 bar plus mod Z2 bar, and you need to prove it. So now we will move to the first one, which is how we'll prove just simply using the property. So you just recall the fact. The fact is basically alpha plus beta, that modulus less than equals to mod alpha plus mod beta for all alpha beta belongs to complex number. So we just use this property and we will prove the first inequality. So here Roman 1, this is Z1 by mod Z1 plus Z2 by mod Z2. So we just use the formula, we just consider this quantity is alpha and second quantity is beta. So this is less than equals to mod Z1 plus mod beta, means Z2 mod Z2. So obviously this will be mod Z1 by mod Z1 plus mod Z2 by mod Z2. So since Z1 and Z2 are both non-zero complex number, so this value will be 1 plus 1. So this is equals to 2. So obviously the first result is proved. So obviously we can write Z1 by mod Z1 plus Z2 by mod Z2. This modulus less than equals to 2. Using this concept, you can prove the second part of this question paper. This is also self-exercise. You can prove it very easily. Now we'll move to the next question, question number 3. Question number 3, this question is very, very important. Actually, this question is given WBSSC, School Service Commission 2019. The question is basically, prove that for a complex number Z, prove that for a complex number Z, mod of Z, this value greater than equals to 1 by root 2 real Z, the modulus of real Z plus modulus of imaginary Z. So this question is very, very important, and this question may be given in any other examination, but it is already given in WBSSC 2019. So you can do more practice so that you can recall that kind of question very easily. So here we just think about how you will prove it, how to think and how to prove. So you just consider z equals to x plus iy, so where x and y are basically both are real number. So then what is x? X is basically the real part of z, and what is y? Y is basically imaginary part of z. Now we'll use the simple formula we have mod of x plus mod of y whole square plus mod of x minus mod of y whole square. That quantity equals to 2 into mod x square plus mod y square. This is a simple thing, so we can prove it very easily. So we can write is 2 into x square plus y square. So now from this line we can write the next line in mod x whole square plus mod y, mod x plus mod y whole square. This is less equals to 2 into x square plus y square. Why? Because the second quantity, this is a square quantity, so square quantity always greater than equals to 0. Mod x minus mod y, that whole square quantity always greater than equals to 0. Since, as we already know, some quantity whole square, say z square, some quantity whole square, that quantity real number. So on that case, we can write x square greater than equals to 0 for all x belongs to real number. Here mod x real number, mod y real number. So mod x minus y is also real number. And if you take the real number square, it may be negative or positive. So obviously it will be greater than equals to 0. So we have this inequality. This inequality we get very easily. So from that we can write mod of x plus mod of y, this quantity less than equals to root 2 into x square plus y square, the square root. So in the next line we can write it as mod x plus mod y by root 2, this is less than equals to x square plus y square, square root. So here you just see what is x. X is basically real z. What is y? Y is basically imaginary z. And what is modulus of z? This is basically root under x square plus y square. So just you put all these values and you will get real z and modulus plus y means imaginary z modulus by root 2. This is less than equals to mod z. So this inequality is very important, and this question paper is given in WBSSC 2009. Here we can use the alternative way. So according to the mth power theorem, so by mth power theorem, just we learned it already inequality chapter. According to mth power theorem, and especially for m equals to 2. So what should be the inequality? The inequality is mod x whole square plus mod y whole square. So this by 2, it is greater than equals to mod x plus mod y by 2 whole square. What is x and y? Where x and y, they are basically the real number. So we can use this kind of inequality and we can easily prove that the questions here, we can easily prove that real z, that modulus plus imaginary z, that modulus by root 2 less than equals to mod z, where z equals to x plus iy, and obviously in that case real z will be x and imaginary z will be y. So you can prove it very easily. That hint is exactly given in a schema of a book, and by using these hints we can prove it. Now we'll move to the question number 4. Question number 4 is also very easy question. And in question number 4, it is given, the question is given like that. Let Z1, Z2 be two complex number, complex number, and omega, that is basically z1 square root of z1 z2 product, and prove that mod z1 plus mod z2, that value equals to z1 plus z2 by 2 plus omega, or you can say the w, no problem, z1 plus z2 by 2 minus w. So how we will prove it? Here we just use one important recall, and the recall is very, very important. Just change the color. The recall is basically z1 plus z2, that mod plus mod of z1 minus z2. So sometimes it happen we can use the inequality like z1 plus z2 whole square, z1 minus z2, that modulus square, this is equals to 2 mod z1 square mod z2 square. We can use this kind of possible inequality. We need to possible equality and properties of the complex number. So now we can start. So just we start from the right side expression, and we can write just in that format. So we can start from right side, but we take the whole square term. Okay. Taking the advantage in calculation, nothing else. So 2 plus omega w plus mod of z1 z2 by 2 minus w. So that square. So that whole square. We can start from this. So that square. This is a plus b whole square, like that. So obviously it will be mod z1 plus z2 by 2, that quantity plus w whole square plus z1 plus, just consider this is a and this is b, so just to simply apply a plus b whole square. So a square plus b square, so z1 plus z2 by 2 minus w whole square plus 2ab. So 2 multiple modulus z1 plus z2 by 2 a whole square minus z1 z2 and modulus. So this value will be again 2, again a plus b whole square. So 2 mod z1 plus z2 by 2 whole square plus 2 omega square plus, just use the formula. This formula is here, 2 mod z1 plus mod z. So just you consider it is z1 and this is z2. So this is mod z1 plus z2 a whole square plus z1 minus z2 modulus square. So this will be 2 multiple z1 plus z2 by 2 a whole square. Just we apply this formula here. So 2 omega square, and the second part as usual, this part I will write in that format, 2 z1 plus z2 a whole square minus 4 z1 z2 by 4 whole modulus. So just we use here the by star. So now then the calculation will be again more simple. So here we can write this is equals to 2 mod z1 plus z2 by 2 whole square plus just a simplification to omega square or w square to mod z1 minus z2 by 2 whole square. So again we just take this quantity to mod z1 plus z2 by 2 whole square plus mod z1 minus z2 by 2 whole square, this quantity plus 2 mod w square. So just again use the formula, 2 mod z1 square plus mod z2 square equals to z1 plus z2 whole square plus z1. Just in reverse way we can use these things. So it will be z1 plus z2 by 2 plus z1 minus z2 by 2, this whole square plus Z1 plus Z2 by 2 minus Z1 minus Z2 by 2 whole square plus 2 W square modulus. So it will be mod Z1 square, then we just calculate it and we just calculate again the second term. This will be mod Z2 square plus 2 Z1 Z2. Why? Because W equals to root under mod Z1 Z2. It is given. So this value will be mod Z1 omega square. So we can write in that format. This value will be mod Z1 plus mod Z2 whole square. So what we get? We get the answer now. So therefore our left hand side was Z1 plus Z2 by 2 plus W, that plus mod Z1 plus Z2 by 2 minus W. So this is equals to mod Z1 plus mod Z2. Okay, because all quantities are in the form of modulus, so all are non-negative quantity. Since all the quantities or each term is non-negative. So obviously there is no negative sign will appear. All sign will be positive in form. So this is the proof, and you can easily prove it. The question number 4. Now we'll move to the question number 5, and question number 5 is basically question number 5. What is given in question number 5? Question number 5, let Z1, Z2 be two complex number, such that Z1 minus 3Z2, that modulus equals to 3 minus Z1 Z2 bar, and mod of Z2 this modulus not equals to 1. Then prove that we have to prove that mod Z1 equals to 3. So generally when we will prove this type of question here, so first you need to think about what is exactly given and what you have to prove. So our given condition is Z1 minus 3Z2. This is equals to mod of 3 minus Z1 Z2 bar, and this is the first condition. And second condition is Z2 that plus not equals to 1. So what we have to prove? We have to prove that mod Z1 equals to 3. So how will we prove it? So this is the questions. So now we'll use the condition, what is given condition. Now it is given that mod Z1 minus 3Z2, this is equals to modulus 3 minus Z1 Z2 bar. So we just take both sides whole square in that form, so that we can calculate it easily. So 3Z2 Z1 bar minus 3Z2 bar. So here just use we have used this formula, mod Z square Z bar, and again Z1 minus 3Z2 whole bar equals to Z1 bar minus 3Z2 bar, and we use also this formula that whole conjugate equals to Z1 conjugate minus Z2 conjugate. So this will be 3 minus, in similar way we use this property, Z2 bar and 3 minus Z1 bar Z2. Here we also Z conjugate, again conjugate, so it will be Z, 2 times conjugate. So now we'll do the simple calculation, the simple multiplication on both sides. So what we'll get? Mod Z1 square minus 3Z1 Z2 bar minus 3 Z2 Z1 bar plus 9 mod Z1 square. This will be 9 minus 3 Z1 bar Z2 minus 3 Z1 Z2 bar plus Z1 modulus conjugate square into Z2 modulus conjugate square. So this will be Z1 square mod Z1 square 9 mod Z2 square minus 9 minus mod Z1 square Z2 square. This value will be 0. So just we will take the common of first from the first two terms Z1 square. This will be first term and the last term, and this will be 1 minus mod Z2 square, and we take the second and third quantity, we take the common minus 9, so this also will be 1 minus mod Z2 square, this will be 0. So this from this we can write mod of 9 1 minus mod Z2 square multiple mod Z1 square minus 9 equals to 0. So it is given that mod Z2 is basically not equals to 1 and mod Z2 is non-negative. And we already know mod Z2, this will be non-negative. Modulus of any complex number always non-negative. So that means that implies 1 minus mod Z2 square, this is non-zero. So obviously mod Z1 square minus 9 equals to 0. So this will be 9. Again we can write this will be mod Z1 equals to 3. It will be plus minus 3, but minus 3 is not appear here because modulus is always non-negative quantity, because modulus is always greater than equals to 0. So we will avoid the minus sign. So the value of mod Z1 will be 3. So here the value of mod Z1 equals to 3, and it is exactly asked in the question paper. You have to prove. So this quantity, this conclusion is done. So today we have done only 5 questions, the first 5 questions of exercise 2A. Next we will continue the remaining question. So in similar way, in each day we will do 5 or 6 questions continuously. So all of you just follow the videos so that you can prepare in a very comfortable way, and you must know different alternative way for solving a different kinds of problem in complex number. And all problems are very, very important because all the problems are very tricky and all questions have been given in some examinations like KVS, NVS, TGT, TGT, and as well as SLST examination. And for obviously the B.Sc course, for complex number, all this question is also very, very important.